everybody. I'm Lisa Miner. This is part two of our second piece of this series of looking at discussing GPCRs, conversation on GPCRs. This particular one is talking about allosteric binding and screening considerations. I work with multispan, and for these presentations, I've been joined by Terry Knacken. And Terry, would you please introduce yourself?
Hi, folks. Yeah, I'm Terry Knacken. I'm a pharmacologist at UNC School of Medicine. I present my comments. I've been studying GPCRs for a number of years, and I present my comments from the point of view of biologists and chemists moving compounds towards drug candidate selection.
That's perfect, because that's exactly what we're trying to do. So, so the first question I have is, in a discovery project, you may want to look at allosteric agonists and antagonists. So there's only activity basically at the receptor when the natural ligand is present. How does that compare to orthologues? What is an allosteric modulator, essentially?
Right. This is a exploding field in GPCRs. GPCRs are nature's prototype allosteric molecule where compounds bind to one site to affect the interaction of the receptor at another site. So as shown in the first slide, we have separate binding sites. And this is what underscores allosteric activity. So the question is, how does this occur? The next slide shows, well, an allosteric compound binds to the receptor and makes stable a unique conformation of that receptor that has an altered activity towards the natural hormone or the neurotransmitter. The next slide shows the number of properties that allosteric compounds can have that actually make them very attractive as therapeutic targets. The last one I show in red because it underscores how allosterics can basically bind to any site on the protein. This does two things. One is it makes the hit rate in an allosteric screen higher than in a standard orthosteric screen because molecules can basically bind anywhere. But the second idea leads to a potential issue with trying to confer human receptor activity on animal receptors. The next slide shows an example. Here we have GPR40, and it has three separate allosteric sites. So this just shows how there's more options now for differences in amino acids between human and animal to cause differences in allosteric effect, and these can be quite serious.
So Terry, how sensitive are allosteric binding sites to changes in amino acids? You showed before that binding sites can be extremely sensitive, but what about allosteric binding sites?
Actually, every bit as sensitive. We saw how a 99.8% difference in amino acid homology can cause serious differences in effects. The next slide shows an allosteric compound. It's a positive allosteric modulator, PAM, which potentiates muscarinic activity. And so we see a wild type effect, get a leftward shift of the concentration response curve. Such effects might be proposed to be useful in cognition for schizophrenia. However, as you see on the panel on the right, a single amino acid substitution completely destroys this activity. So it shows it's every bit as sensitive to differences in amino acid composition as the orthosteric site. Moreover, the next slide illustrates how we don't need to be seeing these differences near the binding site of the compounds. Receptors generally change their state. You have binding at one site to cause differences in many sites. And so we can now think about how the binding or difference in activity at one site can affect the activity of the receptor on signaling proteins, for example, G proteins and beta-arrestin. The next slide shows an example of this, CB2. Now, differences in such signaling lead to the effect of signaling bias, which is a potential therapeutic application of different ligands. So what you see on this slide on the left are effects of CB2 mediating cyclic AMP, and we see no differences between human and animal receptors. On the right, however, we see that with the mouse, we see a difference in the beta-arrestin effect. What this will translate to is any bias that we've measured in the human receptor will not translate to the mouse. And so we will have a discordant prediction of signaling. The next slide shows another example of this. This is the D2 receptor, and what we see are responses to dopamine and DPAT, and the wild type natural bias for cyclic AMP and ERK. However, again, a single amino acid poses catastrophic effects on this natural bias. As you see, we now completely change the relative bias effect for these two pathways. So differences in human and animal receptors can confer differences, of course, in binding, differences in allosteric effect, and certainly differences in biased signaling.
That's really interesting. It basically highlights the need for understanding what you need to do to take your molecules into animals.
Yep.
And so our next series, our next presentation, will discuss how do you take these molecules into animals and what considerations do you have. So thank you, everybody. I'll look forward to hopefully you watch our next presentation.